Let's look at the voltage division associated with the series connection. And here we have n elements connecting in series. We have the voltage for each labeled. And let's see if Vs is given the total voltage Vs, and we're trying to find the one of these voltages. Maybe let's see called V sub Ks. So this is the total voltage, and we can use the voltage division without really calculating all the current stuff. Okay, so let's see how we can get this quickly. And we know the Vk is based on what we label here. This current here is I sub k s times Z sub ks. Right. Of course, all the impedance are known. Okay. And in this case, since the I sub k is equal to total Is, right? So I can replace I sub k by Is, the total current, because these elements connect in series, and therefore Z sub ks. And we also know Vk and Vs, Vs and I sub s are related by the equivalent impedance. Right, I sub s times Z eqs, and Z sub eqs is the equivalent impedance. We know that's just sum of all the n impedances, and therefore we have I is equal Vs over Z sub eqs. So therefore I can substitute this back to here, and what I get is V sub ks is equal to Vs over Z eqs, right, times Z sub ks. Or if I write slightly different, so I can put a Z sub ks here, and Z replaces Z sub eq by all the sum of the impedances, Z sub 2 and plus Z sub ns. And then I need to multiply the total V sub s. Right. So that's how I can get the voltage division. Basically, if you find the voltage across one of these element, and you just use that impedance divided by the total impedance. And then the one caveat here is you have to be careful about this, right? So here Vk, let's see if you go this direction, right? V sub ks is a rise, is a drop, and the total voltage here is a rise, right? So you have to be careful. If somehow you label both are voltage rises or voltage drops, in that case you will end up with negative sign. Okay, we will look at an example and to illustrate that point. So that's very, very important. So here all the voltages here we labeled in terms of the the opposite direction of the voltage. So in that case, let's see if you want to find a V2, and V2s is just equal the Z sub 2 over the Z eq, which is Z1 plus Z2 plus Z plus Zn s times the total voltage V sub s, Vs. So just to be very careful when you apply this voltage division rule. Okay, let's look at an example here. Have a few more minutes. So the example here is I have a voltage source. I have the R and L, C connecting in series, and the circuit is given in time domain, right? So everything in time. So the Vs is step function 10 ut. That means step to 10 volts at t equal to 0. Now you have the resistance 2 ohms, 1 millihenry, 1 millifarad for the capacitance, and the circuit are with 0 initial conditions. So this is very important condition you give. So in this case, when you translate to transform it to the S domain, the things become simpler, right? So you don't have to take care of the the initial conditions. So initial condition means V sub L 0 is 0 and V sub C 0 is 0. So this is what the initial condition means, right? The initial 0 initial conditions means this. For all the voltages you have, for all the capacitors and inductors, they have 0 the voltage and 0 current at t equal to 0. Okay, and now we're trying to find the equivalent impedance seen by the voltage source. Of course, you're talking about that's in S domain. So we transform this circuit into S domain. So the voltage source will become the function of S. So so this is the Laplace transform of V sub st, and the impedance here we have Z sub R, S, and Z sub LS, and we don't have any current associated with I sub LT, right? So this is the and we don't have any initial condition associated with the capacitor voltage either, because we have 0 initial condition. So we have Z sub CS only, and the voltage we're trying to find was, so I want to label that also as well, is V sub L. So in this case, that's going to be V sub LS, and the voltage here is going to be V sub C capital S, because we use the capital to in the S domain that correspond to the lowercase time domain signals. And let's see, in this case with the impedance, by the way, when we transform this in the S domain, the V sub S, that should be equal Laplace transform V sub t, that's Laplace transform of V sub st, that's just equal 10 over S, right? Ut is Laplace transform of ut is 1 over S. 10 ut is 10 over S. And so the Z sub R, S is still R, that's equal to, and Z sub LS, that's just equal LS. And I think we have 1 millihenry, right? So that's 0.001 S. Z sub CS, that's equal 1 over CS, right? And that's equal 1000 over S, because 1 millifarad, right? So that's the so that's the Laplace, that's the element in Laplace domain, right? So the first one here is very easy, because the Z sub EQS is just equal the sum of the ZRS plus Z sub LS plus Z sub CS, which is 2 plus 0.001 S plus 1000 over S, or 1 over 0.001 S, right? So this is the equivalent impedance. What about the voltage? Let's see, the voltage here is the voltage here, let's do the voltage division, right? So let's see the voltage Z sub, let's do the easy one. So B Z sub C S. Let's see, look at the way we're labeling the V sub C and VS. So one is voltage drop, the other one is voltage rise. So in this case, we just use, oopsies, I wrote Z sub C. So V sub CS, that should be equal to the impedance Z sub CS divided by Z sub R plus Z sub L plus Z sub CS times the total voltage, right? So you can substitute the values we have. So we have 1000 over S divided by 2 plus 0.001 S plus 1000 over S times 10 over S, right? So you can work this out, and also if you multiply if you multiply S and if you multiply 1,000 S, if you multiply 1,000 S, what do you get? You get 10 to the power 6, 1,000 S, you get S squared plus 2,000 S plus 10 to the power 6, right? So in this case, what we get times 10 over S, and you can take the inverse Laplace transform of the, you can do the partial fraction expansion. The partial fraction expansion of this one here is, if you do the partial fraction expansion, I did this calculated before, so you can just do all the way as we had before to find the residues. That's equal S plus 10,000 plus 1,000 and minus the power fourth of S plus 1,000 squared. And here you can do the inverse Laplace transform, and the V sub Ct is the inverse Laplace transform of V sub Cs, right? So in this case, you have ut, 10 ut, and minus 10 times e2 minus 1,000 tut, right? And this is based on the S-domain translation property, right? And the last one here is time minus 10 to the power fourth, and you have in this case you have the ramp function, because the 1 over S squared, that's the ramp function, right? So you have e2 minus 1,000 t and the t times ut, and that's the inverse Laplace transform, or the voltage across the capacitor. Let's look at the voltage across the inductor. The inductor here, this voltage labeled the way not the same as when we derive the voltage division, right? So in this case, if you look following this direction, so this voltage rise, and to the V sub L from the negative to plus, that's voltage rise. And V sub S also, I should use V sub S here. Did I use any inconsistent somewhere else? So in this case, we should put negative sign there, because this one is not in that direction. So in that case, we have V sub L S should be equal negative Z sub L S divided by Z sub R plus Z sub LS plus Z sub CS times V sub S. So in this case, we substitute everything in. We got negative 0.001S divided by 2 plus 0.001S plus 1,000 over S plus 10 over S. So I'm not gonna calculate this all the way to, so you can also do the inverse, you can do the partial fraction expansion and then do in the inverse Laplace transform, right? So you can do this, the partial fraction expansion, and then do the inverse Laplace transform, and find the V sub LT. Okay, so that's for the voltage division. I hope this example will illustrate that when you apply this voltage division rule, you need to be very careful, right? Let's see how these two voltage, you will find the voltage across a particular element with respect to the voltage of the total voltage you are given. If the total if both voltages are voltage rises or voltage drops, in that case you need to put a negative sign, right? Otherwise, this should be a very easy rule to apply. I'll see you in the parallel connection.